Okay, good day. So for this video, we're going to solve some example problems related to waves. Okay, so we have problem number 1. So we have a transverse mechanical wave that propagates in the positive x direction through a spring with a constant wave speed is shown. So the medium would oscillate between a positive and a negative amplitude around our equilibrium position. So the wave at 0 seconds is represented by our dotted line, okay, and the wave at 3 seconds is represented by this wave, which is the solid line. So assuming that the wave has not traveled more than a q wavelength in this time, we will determine the wavelength, the amplitude, the propagation of wave, and the frequency and period of our wave. So given now this diagram of the waves, we are going to solve for our letter E, the wavelength. So as we have defined, the wavelength is simply the distance between 2 points of the same property or of the same phase. Okay? So for our solution for letter E, we'll just be determining it from our graph. So basically, the wavelength now is represented by this yellow line. So with that, we'll just see what is the distance between the 2 points. So from the graph, it is now seen that the wavelength is equal to 8 centimeters. Okay? So next, we have our amplitude. So for the amplitude, it is the maximum distance from our equilibrium position. So for letter B, we'll just measure it from 0 to the highest point, and the wavelength now, or the amplitude, is equal now to 6 centimeters. So for your amplitude, this one now will be a positive or a negative value, as the amplitude is moving either going to the maximum positive height or to the maximum negative height. Okay? So next, we have our speed of propagation. So for this speed, we cannot use our general equation, which is the frequency times the wavelength, as we do not know yet our frequency. So we'll be basing now our computation from motion, in which speed is defined simply as the change in position divided by the change in time. So we'll be using now the distance or the position of the object at time 3 minus the position of the object at time 0 divided by 3 minus 0, or the change in time, which is 3 seconds. So from the graph, where is now our position at 0 seconds? So basically, at 0 seconds, our object is at this point. So at 3 seconds, nasaan na kaya tong point na to? So yung point na to, at 3 seconds, so saan ba yung start ng object natin? So this is the 3-second wave. Okay? So meaning, this one now is our 3 seconds. Okay? So na-move yung point na to after 3 seconds to this point. Okay? So basically, the distance now, okay, between time 1 and time 2 is now equal to 6 minus 0 divided by 3 seconds. So giving us a value of the speed, which is equal to 2 centimeters per second. So saan nakuha yung 6? Ito. May 6 minus 0. Okay? And the change in time is 0 seconds minus 3 seconds. Okay? So, let's move to the next question, the frequency. So, the frequency now is our number of cycles per unit time, or we can take it from our general equation, v is equal to the wavelength times the frequency. So we're given, or we have solved already for the wavelength and our speed. So we just substitute our values. So we have 2 centimeters per second is equal to 8 centimeters times the frequency, where the frequency now is equal to 0.25 per second, or 0.25 hertz. And the last required, we have our period, which is simply the reciprocal of the frequency. So that's 1 over f. So the period now is equal to 1 divided by 0.25, or that is 4 seconds. Okay? So let's move to the next problem, number 2. We have a transverse wave on a string defined by the wave function y is equal to 0.2 sine of pi over 6x plus 3 pi t, where x and y are in meters and t is in seconds. Determine the wavelength, the amplitude, the frequency, the speed of propagation and its direction, and the speed of the wave when it is at t equal to 0.25 seconds and when the particle is at x equal to 1.5 meters. So let's have summary of our given. So we're given the equation 0.2 sine of pi over 6x plus 3 pi t. So basically, our solution will be revolving this equation. So for our solution, we now see that the given equation is an equation of our sine wave, which is y is equal to a sine of kx plus omega t. Okay, so from the given equation and the general equation of a sine wave or a sinusoidal wave, we'll now be able to determine our wavelength. So for the wavelength is lambda. Okay, so where can we get the lambda? Wala namang lambda dito sa equation natin. So remember that k is equal to 2 pi divided by the wavelength. So okay, so for the wavelength, in order to solve for this, we have to determine first k. So where are we going to get the k? So the k will be taken from our equation. So we have here the k values. So from the equation, kx now is the same as pi over 6x, in which k now is equal to pi over 6. So equating now this value in the equation, so we'll have pi over 6 is equal to 2 pi over the wavelength, giving us a value of 12 meters. Okay, so next we have the amplitude. So for the amplitude, we have simply our a. So from the equation given, a now is simply equal to 0.20 meters. And we have for our frequency, so the frequency f is not given, but we know that the omega is equal to 2 pi f. So in this case, we have to determine from the equation what's the value of our omega. So from the equation, omega now is the same as 3 pi. So equating 3 pi equal to 2 pi f. So we'll have pi would cancel out. So pi cancels out. So we'll have frequency is equal to 1.5 hertz. Okay. So next we have letter. So okay, so continuing our solution for problem number 2, we want to solve for the speed and direction of our propagation. So for the speed of propagation, now since we know we have computed already our wavelength and frequency, we could simply use our general equation, which is the speed equal to wavelength times frequency. So substituting now the values that we have computed in the previous slide, we'll have 12 meters times 1.5 hertz or 1.5 per second will give us a value of 18 meters per second. So this is the magnitude of the speed. So what is now our direction. So the direction now will be taken from our equation. Okay, so from the equation, we can see that we have here a positive 3 pi t, which is a representation of the positive omega t. So since positive omega t tayo, so the positive sign there would indicate that the direction of the speed is moving at the negative side. So for letter D, the speed of propagation is 18 meters per second and its direction is in the negative direction. Okay? So let's move to the last question. The speed of the wave when it is at 1.5 meters at a time of 0.25 seconds. So for letter E, we cannot simply substitute these values in the given equation. Why? Because the given equation is the equation for the displacement. So the y is your vertical displacement. So in this case, we'll have to solve for the speed by the derivative of y. So for the derivative of y, this is now equal to the derivative of the equation 0.2 sine of pi over 6x plus 3 pi t with respect to time. So from your calculus, time ang ating basis. So ang kukunan ko lang ng derivative is yung time natin. So with this, we'll have now 0.2 times the variable of time, which is 3 pi. Derivative of sine is cosine. So that will now be pi over 6x plus 3 pi t. So this is now our equation for the speed of the wave. Okay? So at any time. So since we're given now the value of x at 1.5 and t at 0.25, we'll just substitute our value. So that will now be 0.6 pi cosine of pi over 6 times x plus 3 pi times time, which is now equal to negative 3 over 5 of pi, that's meters per second, or that's also equal to 1.885 meters per second. And it is in the downwards direction. So what does it mean? So if we're going to draw our wave, okay, so this is our equilibrium position. So it is at this side. Okay, so it is moving in the negative direction. So if we're going to solve for our y also, mas malalaman natin kung nasa ang banda yan. So if I'm going to compute for y, the y is equal to 0. So meaning, our particle now is at 0. So this is the 1.5. And this is at time equal to 0.25 seconds. So it is moving downwards. Okay? So also, in computing for your speed or your y for waves, okay, this should always be in radian mode. So your calculator should be in radian mode. So kung ayaw yung radian mode, you have to convert your angles in degrees. So don't forget, it should be in radian modes. Okay, so let's move to the next problem. So we have problem number 3. A transverse wave on a string travels at a speed of 20 meters per second. This string has a total length of 30 centimeters and mass 100 grams. Determine the tension applied on the string. So if a force 10 newtons is applied on the string, how fast would our wave vibrate? So for our solution, let's have a summary first of the given. So we have the speed at 20 meters per second. We're also given the mass at 100 grams. And we're given the length at 30 centimeters. Okay, so you want to solve for the tension. So for the tension, that is now for strings, we know that the speed of strings is given by the square root of the tension divided by the mass or linear mass density. Okay, so we're given the speed, but we do not know our mu or your mass density. Okay, so what we will do is to solve first for our mu, which is now computed as mass over length. So we're given the mass over length, so direct substitution na lang. So mu now is equal to 0.1 divided by 0.3, or that's equal to 0.33 kilograms per meter. So substitute this value in our equation. So we'll have 20 meters per second is equal to the square root of t divided by 0.333, or the tension now is equal to 100 or 1333.33 newtons. Okay? So if we have now a force 10 newtons applied to the string, how fast would the string vibrate? So we'll still use this equation, but instead of using the computed tension, we'll use the given force. Okay, so for that, we'll have T is equal to 10 newtons. So the speed now is equal to 10 divided by 0.333, or the speed now is equal to 5.478 meters per second. So as you can see, for vibrating strings, the larger the force applied, the faster our vibration would be. Okay, let's have number 4. A 3-meter long wire of mass 150 grams is fixed at both ends. The string is pulled with a tension of 250 newtons. To produce a second overtone, determine the speed of propagation, the wavelength, and frequency produced. What is the fundamental frequency of vibration? So for this problem, we're given the mass of 0.15 kilograms, length is 3 meters. We're given the tension for the second overtone is 250 newtons. So what we would like to solve is the speed of propagation. So for the speed, that would simply be equal to, as we have said, for strings, that is equal to the square root of tension divided by mu. Okay? So no matter what our harmonic or overtone is, remember that the speed is a constant value. So meaning, kahit na anong frequency pa siya, yung speed ng vibration ninyo is still the same. Okay? So, in that case, we could simply use the given tension. So, no need to identify the tension in the fundamental frequency. So, substitute lang. But before that, we compute for your mu, which is m divided by L. And that's equal to 0.05 kilograms meter raised to negative 1. So the speed now will be equal to the square root of 250 divided by 0.05, giving us a value of 70.71 meters per second. Okay? So next, we want to solve for the wavelength. So how are we going to solve for the wavelength? So for the wavelength, we need our frequency in order to use our general equation. Since we do not know our frequency, okay, so pero alam natin that it is moving, or the given is at the second overtone. So, okay, so second overtone now for a vibrating string is the same as our third harmonic frequency. So that is taken from the equation n is equal to x plus 1. Okay. So if we're going to draw that, this is our second overtone. Okay. So from here, we could take our wavelength in terms of the length. So the length now is equal to 3/2 of the wavelength. So we have one whole wavelength and another half. So substituting now our length, we could solve for the wavelength. So the wavelength now for the third harmonic frequency is equal to 2 meters. Okay, so that is the wavelength for the third harmonic or your second overtone. Okay, and for our frequency, that will now be solved by our general equation. Wavelength times the frequency is equal now to 70.71 is equal to the wavelength 2 meters. So F3 now is equal to 35.35 Hertz. And what is now our fundamental frequency for the vibration? That is simply equal to 3 times F1, or this came from our equation N times F1. Okay, so from here, F3 is 35.355, so equal to 3F1, so just divide it by 3. You'll be able to get the value of F1, which is 11.785 Hertz. Okay? Or if you want a longer solution, you can solve for your wavelength for the first overtone. Okay? So another solution, you can solve for V is equal to the wavelength times Fn, wherein the wavelength now is equal to 2 times L from our discussion. So the wavelength now is equal to 6 meters. So V is constant at any frequency or at any wavelength. So we'll have 70.71 is equal to 6 meters times F1, or F1 now is equal to 11.785 Hertz. So it is of the same value. So any will do. But this is the shorter version. Okay? Okay, let's have example number 5. We have an aluminum rod clamped at one end produces a third overtone of 2000 Hertz. So for this problem, we want to determine the speed of propagation, the wavelength, and the length of the aluminum rod. So we're also given the Young's modulus and the density of aluminum. So in this case, the only given is our frequency for the third overtone. So for our solution, since we want to solve for the speed of propagation, no wavelength, is given, so we cannot use our general equation, which is speed equal to wavelength times frequency. But we are given the Young's modulus and density, and we know that for a rod, the speed is also computed as the square root of your Young's modulus divided by the density. So since we're given now the values of your Young's modulus and density, direct substitution. Okay, so but before we direct substitute, we have to convert first the 69 GPa into pascals para consistent yung magiging unit ninyo. So for Young's modulus, that will now be equal to 69 times 10 raised to 9 pascals. Okay, so once you have converted this, direct substitute na lang, so that will be the square root of 69 times 10 raised to 9 divided by 2,700. So computing for the value of the speed, will arrive at 5,055.25 meters per second. Okay? So next requirement is the wavelength. So how are we going to solve for the wavelength? So the wavelength, we're given the speed, we're given the third overtone or the frequency of the third overtone. So we could simply use our general equation. So substituting this, we'll now have 5055.25 is equal to the wavelength times 2000. So we'll arrive at a wavelength of 2.528 meters. And take note, this value now is the wavelength of our third overtone. So the wavelength will change again if we have a different harmonic or a different overtone. Okay? So this will be for third overtone. So next we have for the length of the rod. So for the length of the rod, we would like to draw the wave pattern for it to help us in our analysis. So but before we could draw our wave pattern, we have to identify first what harmonic is the equivalent of our third overtone. Okay? So we know that the third overtone is X, which is now equal to 3. And from or for rods or vibrating rods, the harmonic number N now is equal to 2x plus 1. Substituting x in this equation will now arrive at N equal to 7. So meaning the third overtone is the same as the 7th harmonic of a rod clamp at one end. And for a rod clamp at one end, we have a fundamental frequency na ganito. So 1/4 of the wavelength. Okay? So 7th harmonic siya. So ibig sabihin, kailangan ko ng 7 na fundamental frequencies. 7 na ganitong pattern. So I will have here 1, 2, 3, 4, 5, 6, 7. Okay? So that is my wave pattern for the third overtone. And to solve now for our length, okay, so that will now be equal to 4L over 7. Okay, or this came from L is equal to 7 over 4 of the wavelength. So we have computed for the wavelength of the third overtone. So we could now solve for the length, which is now 2.528 equal to 4L over 7, giving us a value of 4.424 meters. So, okay, that's it for number 5. So we have the next example, number 6. We have a 2 mm diameter rod, 2 meters long and 200 grams in mass is clamped at the center. A longitudinal wave moving at 20 meters per second is produced. An elongation of 10 meters is produced also during the vibration. Determine the first 3 wavelengths, the frequencies produced. So you also show a diagram of the mode of vibration or the wave patterns. So determine the force required to produce the wave. So for this problem, we want to determine the first 3 wavelengths. So meaning we have the fundamental frequency, your first overtone, and your second overtone. Okay? So for this, we want to draw our diagrams first, or your modes of vibration. So for a rod fixed at the center, okay, so we have for your fundamental frequency, we'll have a wave pattern like this one. So x is 0. So n is equal to 2x plus 1, or this is our first fundamental or first harmonic or the fundamental frequency. So for our first harmonic, we know that the length now is equal to 1/2 of the wavelength. Okay? So wavelength is also computed as 2 times L. So 2 times the length given, 2 meters. The wavelength now is equal to 4 meters. So, ganun lang kadali yun. So, let's move to the next wavelength. So, the second wavelength or the second overtone, okay, we'll have it as 1, 2, 3. Okay, or that's x1. So, overtone is 1. So, following the equation, n is equal to 2x plus 1, we'll have the harmonic number as 3. So this is our third harmonic. So the first overtone is our third harmonic. So we have 1, 2, 3 fundamentals. So the length here now is equal to 3/2 of the wavelength. Or the wavelength now is equal to 2/3 of the length. So the wavelength now is 2/3 times 2, or that's equal to 4/3 meter, or 1.333 meters. Okay. Let's move to the next one. So we'll have x is equal to 2, your second overtone. We follow your equation, n is equal to 2x plus 1. So we're going to have an n equal to 5, in which this is now our fifth harmonic. So meaning if we're going to draw our wave pattern, I should have 5 na ganito, na fundamental. So I will have 1, 2, 3, 4, 5. Okay? So for our length, that will now be equal to 5 wavelength divided by 2. Or the wavelength now is equal to 2 divided by 5 times L. Or the wavelength now is equal to 4 divided by 5 meters. So we have solved for the wavelength already. So next, we solve for your frequencies. So we're given the speed of propagation. The speed is constant at any frequency or wavelength. So we'll just simply use our general equation. The speed is equal to wavelength times the frequency. So for the first harmonic, V is equal to F1 times lambda 1. So we'll have 20 is equal to F1 times 4, or F1 now is equal to 5 Hertz. Same goes. We have F3 lambda 3 will be equal to 20 equal to F3 4/3, or F3 now is equal to 15.04. Okay, or simply 15. And lastly, we have F5 L5, okay, giving us an F3 or F5 equal to 25 Hertz. So that's for the wavelength and the frequency of our first three wavelengths. Your fundamental, your first overtone, and your second overtone. So continuing our solution, we have solved already for the wavelengths and frequencies, and we have drawn our diagram of the vibration. So for the first required, what we will do is that we are going to use the other equation for speed, which is the square root of the Young's modulus divided by your rho. Okay, so we know your speed, but we do not know our Young's modulus and our rho. So but we're given the mass, and we can solve for the volume. So for the volume, that will now be 2 meters times the area. Okay, so sa area, we also to solve this. So for the area, we'll simply solve for the area of the rod. That's now pi d squared divided by 4. We're given the diameter, so we could simply solve it as pi times 10 raised to negative 6 square meters. So substituting the area, we get your rho. That's 31,830.989 kilogram cubic meters. So pag na-solve na to, we know already your speed. We can now solve for your Young's modulus. Okay? So for the Young's modulus, that is now equal to 12,732,395.6 pascals. Okay? So in order to solve for the force, we know that the Young's modulus is equal to FL divided by AE. So we know the Young's modulus. Okay? So we know our Young's modulus. We know the length. We have computed for the area, and we're given the elongation or the deformation. So we could simply now solve for your force. So that is now equal to, force is 2 newtons, meaning you are required now to apply 2 newtons in order to produce a speed of wave which is 20 meters per second for the given rod. Okay, if the diameter or the length of the rod changes and also its mass changes and the material changes, then the force will also be varied. Okay? So, basically, the speed of propagation would depend now on the material you are using. Okay? So, let's move to, okay, let's have number 7 problem. The speed of sound waves in air is found to be 340 meters per second. Determine the fundamental frequency of the sound in open air column with a length of 675 millimeters. What is the wavelength of the third overtone? Given now are the speed of the wave at 340 meters per second, and we're also given the length of the air column at 675 millimeters. So for are required, we want to solve for the fundamental frequency and the wavelength of the third overtone. So for our solution, for letter A, the wavelength or the fundamental frequency of the first overtone, or that is your first harmonic frequency. Okay, so to solve for this one, we'll have to draw our diagram. So this is the wave pattern for the first harmonic for an open air column. So we're also given the length, which is 6.75. So from this diagram, we could write that the length is equal to 1/2 of the wavelength, giving us the equation wavelength 1 is equal to 2 times L. So in that case, the wavelength now is equal to 1.35 meters for the first harmonic. Okay? So bakit ko kailangan ng wavelength? Because I will use this in our general equation, which is now equal to V equal to wavelength times the frequency. Okay? So substituting now the speed given and the computed wavelength, we can solve for the frequency, which is now equal to 251.85 Hertz. Okay? So that's for our fundamental frequency. So next, we want to solve for the wavelength of the third overtone. So for the wavelength of the third overtone, we now have the third overtone equal to X. So we identify first our harmonic number. So the harmonic number now for an open air column is equal to X plus 1. So therefore, the third overtone is the same as our fourth harmonic frequency. So pag fourth harmonic frequency, ibig sabihin, kailangan ko ng 4 na ganito. Okay? Or, from our discussion, we could write now that the wavelength for the fourth harmonic is equal to 2L divided by 4. So, saan nanggaling yung equation na to? This came from the equation, the wavelength of any harmonic is equal to 2L divided by N. This is for open air column. Okay? So with that, we're given the length, so we can compute now for our wavelength. And that will give us a value of 0.3375 meters. Okay? So kung nakalimutan nyo man yung equation na to, you can always rely on your diagrams. Okay? So pag magre-rely tayo sa diagram, so we need 4 fundamentals. So we need 1, 2, 3, 4. So if this is our length, so the length now is equal to how many wavelengths can you see? We have 1, 2. So we have 2 wavelength. Okay? Or the wavelength now is equal to L divided by So, tama. 2 divided by 4 is also equal to 1/2. So, you'll also get this. So, 675 divided by 2 is also 3375 meters. Okay? So, you have two options to solve for this. So, either use the equation, or you draw your wave pattern. Okay? So, let's move to the next one. So, let's solve the next problem. We have 7.b. So, this problem is almost the same as the previous problem, but the only difference is that instead of having an open air column, we'll have a closed air column. Okay, so for this, we're still given the speed of the wave at 340 meters per second. We have the length of the air column at 675 millimeters. So we required the fundamental frequency and the wavelength of the third overtone. So for our solution, so we would like to solve for the fundamental frequency of the sound in a closed air column. Okay, so same process, we also solve for the wavelength of the first harmonic frequency. Okay, so to do that, we will now be drawing our fundamental frequency or the mode of vibration for the first harmonic. Okay, so for a closed air column, this is our fundamental. So from this diagram, we could see that the length is equal to 1/4 of the wavelength. So with that, we could get the equation wavelength of the first harmonic is equal to 4 times L. So substituting now the value of L, we'll now be able to get the value of the wavelength for the first harmonic as 2.7 meters. And from here, we can now use our general equation, which is the speed is equal to the wavelength times the frequency. So the wavelength now, or the speed, which is uniform for any frequency or any wavelength, 340 meters per second, is equal to 2.7 meters, your wavelength, times our frequency 1. So the frequency 1 is now equal to 125.926 Hertz. Okay. So next, we want to solve for the wavelength of the third overtone. So for a closed air column, given now our overtone number x equal to 3, so we'll have our harmonic number, which is 2x plus 1, giving us a value of 7. So the third overtone of a closed air column is the same as its 7th harmonic frequency. So with that, from the equation, we know that our wavelength for the fundamental is 4L. Okay? So the wavelength of the third harmonic or the third overtone or 7th harmonic now is equal to 4L divided by 7. So saan naman nanggaling ulit ito? This came from, for a closed air column, the wavelength for any harmonic number is equal to 4L divided by the harmonic number. So our harmonic number is 7. Kaya 4L divided by 7. So with that, we'll have now the wavelength at the third overtone will be equal to 0.386. So that is 4L, 4 times L, 0.675 divided by 7 is 0.385, 7 or 386. So again, kung ayaw nyong tandaan nito, you can always draw your wave pattern. So 7th harmonic frequency, so I need 7 fundamentals, so I'll have 1. So 1, 2, 3, 4, 5, 6, 7. Okay? Ayusin natin. So I'll have I'll have 1, 2, 3, 4, 5, 6, 7. Okay. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So this is your L, which is equal to 1/4 of the wavelength times how many 1/4 are there? 7. So will arrive at the same value of 0.386. Okay? So next, we have the next problem, number 8. So a tuning fork vibrates, producing a sound at a fundamental frequency of 18 Hz in a closed air column. The speed of sound in air is given at 343 meters per second. Determine the wavelength and the temperature that would produce the same frequency when the length is 5% increase. So for this problem, we are given the value of the speed at 343 meters per second. And we're also given the fundamental frequency, or your F1, your first harmonic, at 128 Hertz. So for required, we want to solve for the wavelength of the first harmonic and the temperature if the length is increased at 5%. So to solve this, to solve for the wavelength, we need to use our general equation. Speed is equal to F1 times the wavelength. So since we're given your speed and wavelength, or the frequency, so direct substitution na lang. So the wavelength now is equal to 2.678 meters. So remember again, this one is for your first harmonic only. This will again change if it is a different frequency. So, okay. So, if the length now is increased by 5%, we solve for the length as using first our wavelength, okay, since we are not given the length. So, we know that the wavelength for the first harmonic is equal to 4 times L. So, in that case, the length now is equal to 0.67 meters. So, it's increased by 5%. So, just multiply the length by 1.05. So, the length now that is increased is equal to 0.703 meters. So, if that is our length, okay, so we can solve for the temperature by computing for the wavelength for this case. So, since the length changed, the wavelength will also change. So, using now our equation for the fundamental wavelength equal to 4L. So, the wavelength now is equal to 2.81 meters. Okay? So, same frequency tayo, 128 Hz pa rin. So, the speed now will be the same. So, the velocity will change for the same frequency but different wavelength. So with that, we solve for the speed, which is now wavelength times the frequency. So that's equal to 360.15 meters per second. And we know that for air, the speed is computed as 332 plus 0.6 times the temperature. So equate the two, will now arrive at a temperature of 46.92 degrees. So again, para makuha yung 46.92 degrees, itong 332.6, equate ko siya dun sa na-compute natin na 360.15 meters per second, which is the velocity or the speed. So this is the speed at F equal to 128 Hertz and a wavelength wherein we have a 1.3 or we have a 0.5% increase in length. Okay? Okay, that's it for our problems, example problems for Module 8 waves. So thank you for listening. So if you still need more examples, there are more examples found in your modules.